launch of the first satellite of the second generation, which was called Glonass M, and the first satellite was launched in 2001. Compared to its predecessor, Glonass M satellites had got many improvements, such as a second signal, improved navigation messages with new parameters, which were very useful for practical usage. This were, for example, an estimation of the pseudo-range error. This were information about slot number and some other data fields, which helped a lot for more reliable operation of Glonass as a system. As you know, Glonass is the second GNSS after GPS, which was declared for public use. Before May 2000s, before turning selective availability off in GPS, Glonass positioning was much more accurate compared with GPS one. It led to wide usage of Glonass signals in many applications. Introduction of the first combined GPS plus Glonass receiver has dramatically changed the landscape of surveying and navigation industry. Because of increased redundancy, it became possible to work under challenging environments in which GPS alone positioning didn't perform well. This slide just provides some feedback from, let's say, early days. These are just a few messages from point of the beginning message boards, and it was the period when combined GPS plus Glonass receivers appeared on the market. And this feedback from users told us that Glonass helped a lot for positioning. In particular, it removed gaps in the positioning related to the time periods when, for example, PDOP positioning dilutional precision factors weren't good for reliable positioning. In this case, Glonass played a critical role for continuous and reliable positioning. Since that time, GPS and Glonass positioning became a standard, and later on, Galileo, Beidou, NavIC, GNSS system became available. If we are saying about Glonass current status, currently there are 24 satellites orbiting. They occupy 3 orbit slots with 8 satellites in each of these slots.
Alexei,
yes?
are you not changing the slide?
Sorry?
You are not changing the slide. You are only on the.
So do you see my screen?
First slide only. Your presentation.
Okay.
Yes.
Sir, it is fifth slide.
Where?
Fifth slide.
It is the fifth slide. I have not seen the other slide, previous slide.
Yeah.
Is now okay?
Yes.
Okay, okay.
So first, second, and third was missing.
Ah,
First, second, third, and fourth are missing.
I see,
Sir,
sir.
I think he should present with the presentation icon so that it can be seen in full view size. I mean,
Yes.
then the slide change will be more easy and visible, I think.
Yeah, that is right. But first, he should change the slide also.
Yeah, yeah.
Uh, you please go in a slide presentation mode and then keep on changing the slide. Then you will be able to bigger slide and also change of the slide.
Uh, okay.
Sir, in the bottom panel, there is an icon revealing the presentation sign. If you click on that, it will be in full view mode and slide change will be easier for you, I guess. Yeah, I think.
You click on your dumbbell. In the below there is a dumbbell shape and you click it. Yes, yes. Thank you very much.
Thank you, sir.
Okay. Uh, sorry for that. So this slide was visible, right? And this one as well.
Yes, visible. Please go ahead.
Okay, okay. Um, so if I think about GLONASS current status, once again there are 24 satellites orbiting, occupying 3 orbital slots, and there are 8 satellites in each of such slots. So obviously this number of satellites provide global coverage, and with a good geometric factors, so GLONASS can be used worldwide, including GLONASS only positioning, and the total number of satellites should be enough for reliable positioning. This slide just provides some information about GLONASS ground segment command and control subsystem. It is a typical, I would say, operation for any GNSS system. So there is a network of the stations, uplink and telemetry facilities. Also, it should be noted that each GLONASS satellite is equipped with passive laser reflector, and it's feasible to make laser ranging to all GLONASS satellites, and it improves the accuracy of orbits because it is the most accurate method of ranging. So there is a central facility, system control center, that computes orbits. Also, this network sends raw data to the central facility, and at the time being there are about 25 stations in Russia and about 10 stations abroad that track GLONASS signals. It should be noted that GLONASS shares the same frequency channel numbers, and 2 satellites have the same FCN, so-called antipodal satellites. And it was required because there are just 14 frequency channel numbers allocated, while there are 24 satellites orbiting. This slide contains the GLONASS K space vehicle. It is um, a real sample. There were different generations of GLONASS satellites. First of all, there were satellites belonging to the first generation, but all of them are out of service currently. GLONASS M satellite currently in operation, so almost all satellites of the current GLONASS constellation belong to this type of the satellite. Last year, the first launch of the GLONASS K1 satellite took place, and in accordance with current plans, next 8 GLONASS K1 space vehicles should become available. All of them are in production. The first launch of GLONASS K2 satellites with Cdma signals enabled is expected in the end of next year, and 15 GLONASS K2 satellites are going to be produced. Of course, the lifetime of these satellites is increasing, and currently it is 10 years. A very important feature of GLONASS K2 satellite is that it will support 3 new Cdma signals in addition to legacy Fdma signals on the board. Also, let's talk about orbit parameters of GLONASS compared with some other systems such as GPS and Galileo. We see that the inclination of GLONASS orbits is higher compared with GPS and Galileo ones, and it provides some advantages in the northern regions. So, for example, GLONASS is better suited for Arctic regions, for Scandinavia, Canada, and all such things. Also, the GLONASS orbits are stable. They don't require corrections during operation compared with GPS orbits, because there are gravity field resonances that affect these orbits, but GLONASS orbits are chosen in such a way that this effect doesn't affect orbits significantly. With respect to datum, during 1990s, there was a big difference between a GLONASS datum and WGS 84, mainly just because of the rotation around z-axis. But with introduction of the new datum for GLONASS, it is PZ19 parameters of the Earth. This offset was compensated, and currently PZ 90.11 and WGS 84 datums are close to each other at the level of centimeters. So for all practical applications, they could be considered to be the same. At least no additional Helmert parameters transformation is required when one combines GLONASS measurements with GPS or Galileo ones. And also, just because of the period of revolution, GLONASS may have some advantages in terms of PPP performances, just because of more rapid change of the geometry. This slide provides some picture um, for allocation of the frequency bands for GLONASS Fdma signals. So currently there are two civil Fdma signals in L1 and L2 frequency bands, and also just because of the nature of Fdma signals, they occupy different frequency bands. So there is a difference on the order of 0.5 megahertz between joining frequency channel numbers. Historically, in the beginning, the total number of FCN was close to 24, but then an interference problem with radio astronomy was detected, and it was proposed to shift the frequency band compared with what was originally, and it led to the change in the frequency band, and currently there are frequency channel numbers allocated from -7 to +6. There are 14 of them, and antipodal GLONASS satellite occupy the same frequency channel numbers. Now I would like to talk about specifics of GLONASS with respect to other GNSS systems, and it is a topic that led to quite serious interoperability issues in the past with other GNSS systems. Historically, Javad and Topcon receivers were the first on the market of combined GPS plus GLONASS receivers. Later on, other manufacturers such as Trimble, like Novatel, started to produce combined GPS plus GLONASS receivers, and at the time quite serious interoperability issue was detected, connected with so-called GLONASS carrier phase biases. The problem that originates just from the usage of Fdma signals. In terms of the receiver hardware, the Fdma signals make the receiver hardware more complex compared with Cdma signals. Nevertheless, currently almost all manufacturers of GNSS equipment support these Fdma signals without problems. Also, it is quite serious specific that GLONASS system time includes leap seconds, compared with other systems such as GPS, Galileo, BDU, NavIC, UZSS. All of them have a fixed system time that that isn't affected by leap seconds. Um, um, in principle, it just means that the GLONASS measurements should be processed carefully in order to provide continuous and reliable service during the event of the leap second edition. And in fact, it's already implemented in the user equipment, and it shouldn't lead to problems in the state-of-the-art GNSS equipment. In terms of the usage of navigation, in terms of the usage of GLONASS navigation data, also there is specifics in the sense that we need to use a numerical integration instead of use of close analytical expressions when computing satellite positions. Potentially it may provide more accurate positioning, but again requires careful processing inside user equipment just because of these specifics. Also, in my presentation, I tried to focus on these specifics of GLONASS rather than on a general overview of the system, because all such information can be easily found, and this information is available. But perhaps for this presentation, it would be more useful and more interesting to be focused on the topics related to specifics of GLONASS and how to deal with issues that may originate from these specifics. This slide demonstrates what we had in the past when we tried to work with the receivers of different manufacturers. This slide includes the carrier phase double differences when using the receivers of different manufacturers. So we can see that these carrier phase double differences are not integer, and there are offsets with respect to 0. The offsets which are linear dependent on the difference between frequency channel numbers. So the more this difference, the greater this difference, the greater offset will be with respect to 0 in terms of carrier phase double differences. It led to serious problems in the past, because sometimes we couldn't see provide reliable ticket positioning when using, for example, the base receiver from one manufacturer, combining it with the receiver of other manufacturer, because the ATK position just it was just not feasible to compute this ATK position because of this carrier phase biases. However, all such issues were resolved, and it was a process of standardization of the GLONASS messages within ATCM 104 committee, and in the end we have got 1230 message that provides information about the values of GLONASS phase biases, and this message helps in providing reliable positioning if we use ATK mode between receivers of different manufacturers. So this problem can be considered resolved, and the origin of these phase biases was connected with different time of making code and carry phrase measurements. So this difference, which originated from from digital processing, could lead to the offsets, and it affected carry phase double differences. This topic was resolved in about 27, and currently we shouldn't face any problems with with this topic, because this message type is already standardized, and any network service includes this message type supported. With respect to GLONASS system time, GLONASS system time is defined to be a UTC SU plus 3 hours. In other words, it's Moscow time. As I said, it isn't the case for the rest of the GNSS systems. All of them include all of them support system time, which isn't affected by the events of leap second edition. Currently, there is a difference on the order of plus 18 seconds between GPS system time and UTC, and the difference between GPS system time and Galileo, NavIC and QZSS system time is 0 if we are saying about the system time modular 1 week. GPS and BDU has got 14 seconds, which are fixed. In other words, this difference is not changing with time. So if we know, for example, GPS time, we always can compute the rest of GNSS system time except for GLONASS, because for GLONASS we need to know the current the current difference between GPS and UTC in order to compute GLONASS system time. It is a GLONASS specifics, but I wouldn't say it leads to serious problems, because it is well known, and reliable processing of the event of addition of leap seconds has been implemented in the user equipment, and I can say that it's feasible to process this event reliably, and it shouldn't affect a continuous work of GNSS receivers. Now I would like to talk about methods and steps of numerical integration. It is one more specifics of GLONASS, and for reliable high accurate positioning, it may be important to choose a proper step of numerical integration. This table includes the results of numerical integration using different integration methods, such as Runge-Kutta 4th order, Feldberg 5th order, and Shanks 7th order. Of course, the greater the order of methods of the numerical integration, the more accurate results we obtain. And the same dependence exists with respect to the step of integration, um, the less of this step, the more accurate results we can obtain. In the sense, it's required to choose, let's say, a trade-off between the order of numerical integration and the step of this numerical integration in order to make sure this the numerical errors don't affect computation of Glonass orbits. And if we are saying about high precision, high accurate applications, then the step on the order of 50 seconds could be recommended because it provides an error on the order of um, 0.5 millimeters if we apply integration on time span equal to 20 minutes. So, so this data, this table relate to the results which we obtain when we integrate Glonass orbits on time spans equal to 20 minutes. And now let's talk about Glonass current Fdma and future Cdma signals. It should be noted that both types of the signals will be supported on board of future Glonass K2 satellites because it was of principal importance to provide compatibility with existing equipment. So Fdma signals will be available along with Cdma ones for on board of future Glonass K2 satellites. It's planned that there will be 3 additional Cdma signals with current 2 Fdma signals, and it should provide very significant advantages to a Glonass system compared with current status, just because of obvious reasons, just because of availability of new signals, and they will occupy 3 separate frequency bands, including L3 Cdma, and they will provide improved performances in terms of positioning performances. Currently, we have interface control documents published for all the Glonass systems. There are 3 separate interface control documents for for 3 new Cdma signals. Also, it should be noted that as the so-called SDKM system is available, and currently it is under testing, and it should become available for positioning really soon. SDKM is an S-bus compatible system similar to VAS, EGNOS, GAGAN, and it transmits signal in GPS L1 frequency band, and also L5 frequency band is also planned to be used in the future. So SDKM provides just the standard level of accuracy related to S-bus positioning. And SDKM should be completely compatible with S-bus specifications. It's important to note that SDKM will support GLONASS signals along with GPS ones, and perhaps other GNSS systems will become supported in the future. And if we are thinking about GLONASS future development, currently federal program for further GLONASS development for the period 2021-2030 is being defined. In connection with federal program SPHERE in English, it is ecosystem that includes space-based internet communication, remote sensing, and so on. And by 2030, more than 500 space vehicles are expected orbiting. GLONASS should become an instrumental part of this system. And the first launch of GLONASS K2 with Cdma, as I already noted, should take place next year. There are challenging plans with respect to future GLONASS satellites, and it is known that PPP service will be available on board of future GLONASS satellites. So L3 signal will include a data stream that would allow working in PPP mode, improving the positioning accuracy to up to 1 decimeter level in horizontal plane. It finishes my presentation, and thank you for your attention. I think that if there are questions, we can discuss some topics at more deep level, and if we need to touch some topics, we can do that for during the Q&A session. Thank you, and I'm ready to answer your questions.
Okay, Dr. Alexei,
Yes.
I have one very small clarification. Do you have any other presentation in addition to this?
Do you mean
Or this is
GLONASS?
all?
Do you mean GLONASS development?
Yes.
These are all materials I can provide at the time being.
No, my question why? Because you are supposed to give a talk for up to 4:45, but you have still almost an hour left. If you do not have any other to say, then we'll start the question hour.
It's planned to talk about the about NTLab products in the manufacturer session tomorrow.
Okay. So now, so thank you very much for your presentation. You have given a lot of important information related to the status of the GLONASS. And first, I would request Jaideep to look at the chat box, whether if there is any question, then we can start the discussion. And then I hand over to Jaideep. You please compile all the chat box question and Let us see whether any questions is there.
No, in the chat box at present there are no questions. So I request the participants, if you have any question, please write in the chat box so that we can communicate with Mr. Alexei Zinoviev and he will answer. So
In the
participants,
meantime, by the time, let the participants write on their chat box so that we start the discussion. In the meantime, let me have few questions. Um, and firstly, let me tell you, as my personal experience with the GLONASS in India, I, P. Banerjee, started the GLONASS study way back in 2000, in 1999 in India, in New Delhi. And I should be saying that I was the first person to monitor the GLONASS signal for its capability. That time I had a GLONASS receiver. And we made an extensive study. We prepared the report, and then Dr. Anindra Bose, along with his student, uh, Dr. Shreya Sarkar, they carried out a very extensive study on GLONASS. And I would like to inform you, I don't know whether you have gone through that paper. There was a review paper of 36 years experience on GLONASS in India, published in your country, that gyroscopy and navigation in 2018. And this is a very exhaustive paper on the our experience on GLONASS, and it is written by Professor Anindra Bose, Shreya Sarkar, and myself, and it was published in 2018. Uh, have you ever gone through that paper by any chance?
I could see a presentation by Dr. Anindya Bose related to evaluation of the performances of receivers of different manufacturers, low-cost receivers, I mean.
Okay, that's a different. Okay, now to the related to GLONASS, just for my own understanding, you initially started Fdma probably to get rid of the jamming issues. Now you have now gradually switching over to Cdma. Now
Yeah.
Cdma, is it your future plan that you will rather you'll stop sending your signal in FDMA? You mentioned that in between, for the continuity and for the compatibility of the existing receiver, you will continue for some time. And what I understand from your talk, that you may discontinue using FDMA and you will completely switch over to CDMA. Do I understand correctly?
Um, FDMA signals may provide some advantages compared with CDMA signals in terms of anti-jamming, just because of the different frequency bands. But the current concept is that FDMA signals and CDMA signals should exist together, and there are no plans to switch FDMA signals off at some moment in the future. So in accordance with the current concept, FDMA and CDMA signals will always be broadcast from GLONASS satellites, and there are no plans to switch FDMA signals off at some moment in the future.
Okay, that's fine. It's a good information for us. Secondly, you initially mentioned that you claim that GLONASS orbit is more stable than GPS and no correction required.
Yeah.
What did you do to make the orbit so stable? Because I have also a lot of experience in satellite communication and also in GNSS GPS. So you'll always have perturbation due to many other factors in the orbit, and you say that doesn't require any correction required like GPS might have. So I am curious to know how you make the orbit so stable.
These are just the parameters of the orbits. So they are chosen in such a way that um, the resonance harmonics related to the Earth's gravitation field. Um, these harmonics don't affect GLONASS orbits dramatically. So that's why um, just because of the chosen parameters, these orbits become more stable compared with GPS ones.
Now, let me clarify your answer. I would like to understand, is it because of your specific orbit you have chosen, that is inclinations and other
Yeah,
six
yes,
parameters,
yeah.
or it is a design of the satellite itself that which will which will to some extent counterbalance the effect of the other effect?
These are just because of the orbit parameters such as inclination, um, uh, big semi-axis and all such things. So these are Keplerian parameters of the orbits.
Your parameter specialty one is that you have mentioned is a higher inclination. This may be better suitable for the North Indian region, but
Yeah.
is it the selection of the higher parameter give any advantage to the stability of the orbit?
Uh, yes, I think so. Um, I just cannot identify which Keplerian parameters are the most important, but all of them were chosen in such a way that mm, GLONASS orbits become stable and of course at some level of precision. Of course they are affected by different factors. There is a lot of them. um, so solar winds, for example, anything that affects GLONASS orbits, GLONASS dynamics, and there is a lot of factors which need to take into account when one tries to model the orbit motion, as you know, of course. But the parameters of GLONASS orbits are chosen just in a way that they provide some stability um, in terms of influence of the Earth's gravity field, because it is the main influence um, that affects the parameters of the orbits.
So does it mean that when you send the orbit ephemeris for the calculation of the satellite position at a particular moment, it contains only six parameter and very few number of perturbation coefficients?
Um, um, GLONASS navigation data, they don't include Keplerian parameters. They include just the state vector. So three parameters of the position and three parameters of the velocity, and also there are accelerations. So there are 9 parameters which define GLONASS orbits, and um, GLONASS ICD includes a simple model of the satellite motion um, that need to be used for computing a GLONASS satellite position at at other epochs. And it's recommended to use Runge-Kutta fourth order method of numerical integration for computing GLONASS position at different epochs. It is how it's defined in terms of GLONASS ICD. So it is just a state vector, and in principle we could use more sophisticated models for orbit motion. In this case, we can expect some advantages in terms of precision with which we can compute GLONASS orbits if we use more complex dynamics, more complex models, and all such things. So it, to some extent, it depends on the user. If we apply more complex models, then it's feasible to compute GLONASS position more accurately compared with, for example, with Kepler parameters.
Okay, thank you very much, Alexei Zinoviev, for your excellent explanation to my questions. Now I'll again go back to Dr. Jaideep, and please see whether any questions is there in the chat box, so that he can reply to all these questions.
No, sir. Till now there are no questions, sir. So there is no question.
So, if there is no question, so Alexei, then it is a close of the session, um, unless we continue some discussions on that. So, Jaideep, do you have anything to say on this?
Sorry, it is a question for me?
Jaideep, do you have any questions on issue, or is it the time that we should close this session?
Sir, one question is there now. That is,
Please.
is it true that GLONASS accuracy is better near to polar region than equatorial region?
No, I wouldn't say so. It is just because of the geometry, just because of high inclination. GLONASS satellites could be visible better near the polar regions, but it doesn't mean that the accuracy of GLONASS in polar region is greater compared with equatorial ones. Of course, at equator we can expect better performances just because of the greater number of satellites. In the regions near to the polar regions, the total number of satellites becomes less compared with the equator, and just because of this fact, the accuracy may become worse compared with what we have at the equator.
So, if I understand your reply correctly, so the GLONASS orbit is so designed that its visibility of satellite will have some advantage in northern region than the equatorial region, but there will be no change in the, no deterioration in the accuracy in the equatorial region whenever you have a sufficient number of satellite visible in that area.
Yes, the high inclination just means that GLONASS is visible better compared with other GNSS in the polar regions. But it doesn't mean that the accuracy of GLONASS positioning is worse in equatorial regions compared with other GNSS systems, of course. It just means that the higher number of GLONASS satellites can be visible in northern regions compared with GPS ones, for example, because of the inclination, just because of the orbit parameters. Um, so the elevation of GLONASS satellites is higher compared with other GNSS in the polar regions. It is the only difference in the sense compared with other GNSS.
Okay, nice. It's now clear. Okay, any other in the chat box? I do not see anything. Is there any exact method to solve ionospheric error? Well, Jadid, there is.
Yes, there is another question that is there any exact method to solve ionospheric error?
The ionospheric error can be compensated just because of the just by means of tracking dual frequency signals on both frequency bands L1 and L2, and of course we can build iono-free combination of the measurements that should lead to compensating of ionospheric error, or at least making it very very small. If you mean whether GLONASS broadcasts ionospheric parameters, the answer is no with current Fdma signals, but future Cdma signals will include ionospheric parameters that can be used for single frequency users in order to compensate ionospheric influence.
Well, there is another question in the chat box.
So there is another question from Ismetha that sir, for positional accuracy, is GLONASS better than GPS?
It was a case before 2000s when selective availability was turned on in GPS, but currently GLONASS doesn't provide any advantages over GPS in this sense. I would say that GPS and GLONASS should operate at approximately the same level of accuracy at the time being, but Fdma signals again have some specifics because of the code biases. In the sense, GPS positioning with Cdma signals may be more accurate compared with GLONASS Fdma signals, but it shouldn't be the case with future GLONASS Cdma signals, because in this case no significant code biases will be available in GLONASS measurements, and GPS and GLONASS will operate on the same level of positioning accuracy. But the time being, GLONASS accuracy is slightly worse compared with GPS ones, but if the code biases are compensated, then both GPS and GLONASS can operate on the same level of positioning performances.
Okay, thank you. Jaideep, do you?
Yes, no, sir, no more question.
Okay, if there is no question, let me put my own comment whether you are comfortable to talk on timing application of Glonass. So I have one question related to that.
Yep.
That the time for timing application, you must be aware that you can have a timing solution at a fixed position by receiving a single satellite, not four satellite or five satellite,
Yep.
because the position is a position of the location is predetermined with a very high accuracy, and that is fed to the receiver, and receiver gives the yield. But so that way, being a timing application man, so I extensively use the GLONASS and the GPS and Galileo and all these satellites. So my experience is that there is a question of bias, satellite biases, while you are uh, trying to get the timing application for the any constellation. In this CDMA, you always receive the same frequency except the different code. But in the FDMA, like GLONASS, sorry, if you receive a signal satellite from a GLONASS, then when you receive switchover from one satellite to the other, your frequency changes. So your bias necessarily may change. So that is a serious problem. And how do you have any suggestion how to take care of this?
Again, it originates just from the nature of FDMA signals, and because of non-linearity of the receiver hardware, it may happen that code biases become available for FDMA signals, and these biases may be different for different frequency channel numbers. It is a well-known problem, and in order to overcome it, the most straightforward method to deal with that, I would say, is to calibrate GLONASS receivers with respect to, for example, simulator. Then simulator should have all such biases close to zero, and then we can calibrate the GLONASS receivers with respect to this simulator and compensate this effect just as a result of the comparison simulator and receiver measurements.
So does it mean to say that you'll have to calibrate the GLONASS receiver for all the frequency channel it has? Because if you calibrate a GPS receiver with the help of simulator, it may require to be calibrated for a particular one frequency. Whereas if you would like to calibrate a GLONASS receiver, then you will have to calibrate for different values for different channel. Am I right?
Yes, GLONASS requires calibration for each frequency channel number because it may not be a linear dependence. So in order to make sure that all frequency channel numbers are calibrated properly, we need to see to verify the whole range of these frequency channel numbers, because it may be just the specifics of the receiver hardware, how to perform signal tracking for different signals, and these code biases may affect pseudo-range GLONASS measurements. But but again, it's a well-known problem, and we calibrate our receivers with respect to a simulator, or there are some other methods of compensations of this effect. In principle, it is feasible to do real-time calibration just during the operation of the receivers, and some manufacturers apply this method for compensating these code biases of GLONASS signals.
Okay. So now again I would come back to your higher inclination orbit. You said that higher inclination orbit is better. Is it better only for the northern region visibility or it has any other advantage?
Only in terms of visibility, I would say, um, because it just makes the total number of GLONASS satellites greater near the polar regions, but that's all I would say. I don't know which are the advantages this high inclination
Yes,
may.
okay. Okay, fair enough. If you do not see any other advantage than the visibility in the northern region, it's fine. I just out of curiosity wanted to know whether it has any other advantage. If not, it's fine. Because I know that even in you do not prefer geostationary satellite for communication. You always go for a high inclination. Um, it's a different orbit. You always a different orbit with a high inclination, so that most of the time it remains in the northern region, and very little time in the uh, and also it is a I believe it is highly elliptical.
Yeah,
Your communication satellite. Yeah. Okay. Okay. Thank you. I have learned many things from you on Glonass, so which I didn't have a complete information. Anyway, thank you very much, Jadip. What do you say about this? Do you have any other any other in the chat box? I do not see any other new one.
New questions are not there.
Okay, my request to all the participants, if you have any questions or any queries, let it be a simple one. We have time, you can still give a write on the chat box so that you can get the answer from the experts. We can wait for 2 3 minutes. You take your time to write on the chat box. Even as because there is not much question, the concerned participants may come up on the, they can unmute uh, their speaker and come up and put your question yourselves, as because there is not much question. Okay, I don't see any participants have any queries. So, and Jadip, if you allow me, then I can close the session.
Okay, so I would request you to conclude the session now.
Okay.
Sir.
So, Dr. Alexei Zinoviev, I would like to profusely thank you for giving your presentation and have your patience for um, answering all the questions. Particularly, I have put you a lot of questions. Thank you very much for your patience to answer all my questions. And I believe that by your expertise and your vast experience in GONAS, the participants here got a lot of benefit and they got a lot of information which may not be otherwise always available. Uh, so thank you very much for your time and for your sharing your knowledge and experience to all the participants. Thank you very much and have a nice time.
thank you very much, and I also was
Thank
very
you,
glad
sir.
to present these materials to auditors of this program. So, and thank you for your questions.
And before you go, let me tell you that I think you will not mind if you send you email asking few other questions if that comes up in future.
Okay. Okay.
Okay, thank you. Okay, Jaideep, now if you permit me, I can close the session with a thanks
Okay.
to the speaker and the participants.
Okay, sir. Okay. Now I'll request Professor Parameswar Banerjee to conclude the session for today. So this is the last presentation of today. So now the for today the program is over.
So yes, today the program is over.
So today's program is over. So I thanks all the participants and the experts for their for their valuable participation in this 5-day FDP. Very good evening to all of you. In tomorrow again we'll start at 10 a.m. So I would request all of you to join before 10 a.m. so that we can start at a scheduled time. So by taking the permission of the chair, I am closing the session for today. Thank you all.
Okay, thank you very much, Jaideep. And let us close the session. And thanks all the participants and the speaker.